Welcome to the Getting Started with GeoStudio video series. This tutorial introduces how to use the SEEP W product of GeoStudio 2012. This tutorial video has been designed to help walk new users through the basics of setting up a simple seepage analysis in SEEP W. So if you are new to SEEP W and are not sure where to start, you've come to the right place. The main topics that will be covered in the tutorial will be how to create an analysis in SEEP W by using the Define view to set up the analysis, the Solve Manager to solve the numerical analysis, and the options available in the Results view to gain a deeper understanding of the analysis. So, let's get started. Here you can see some results of a steady-state seepage analysis that was conducted in SEEP W. The results include total head contours, velocity vectors, flow paths in green, and the location of the phreatic surface or zero pressure contour as a blue dashed line. We will now go through the step-by-step instructions for creating this analysis in SEEP W. You can also view the SEEP W tutorial file available on our website, which was created using these steps. We will start on the GeoStudio Start page, where you can create a new project, open an existing project, or click on the appropriate links to view examples, tutorial videos, or engineering books for each GeoStudio product on our website. We will create a new project and choose to create the project using the default International System of Units. If preferred, a blank document can be created with imperial units at this point. Once our new project is created, the Key in Analyses window is opened, where we can add a title to our analyses tree, add an author, or add comments for future users. Now we are ready to add the SEEP W analysis to our analysis tree. We will add a steady-state seepage analysis. Here we can change the name of our analysis if desired, as well as change our analysis type to transient if we decided to not conduct a steady-state analysis. We can also add a description about the analysis to help future users. Next, we will look at the Convergence tab, which shows the convergence criteria for the analysis. Here we can change the maximum number of iterations, the iteration comparison criteria, or the under-relaxation criteria. It is recommended that you view the Convergence and UR tutorial video as a part of the Getting Started with GeoStudio series for more information on what the values of these criteria mean. You can also view information on these criteria by using the online help or the SEEP W engineering book. The equation solver can also be changed in this tab if required. The Time tab can be used to change the time steps and duration of the analysis if we were conducting a transient analysis. As this is a steady state scenario, we will keep the default settings of 0 seconds. Lastly, the Advanced tab can be checked to see what extra options might be available for the analysis. In this case, the option to turn off surface water ponding is available, but we will leave this turned on for our analysis. Next, we will zoom into our drawing page and then take a look at the drawing scale of our analysis. We will go to Set, Units and Scale, and here we can see the units that are being used in our current analysis. Here is where we can change our units if desired. For example, if I wanted to change my time units from seconds to days, I can do it by choosing days in the drop-down menu. The problem extents boxes can be used to help modify the scale of the analysis. Changing these values can change the view of your analysis so that the entire domain remains on a single page. We will toggle off the Calculate Max Extents option and change our maximum X coordinate to 60 meters and our maximum y coordinate to 15 meters. This automatically adjusts our scale values to accommodate these extents. We will toggle on the Calculate Max Extents again and fine-tune our horizontal and vertical scale values to ensure a 1-to-1 aspect ratio. Now we are ready to create our domain. We will start by adding axes to our working area to help visualize the drawing extents of our domain. This is completed by going to Sketch, Axes. Here you can also change the names of the axis titles as well as the X and Y axis extents. We will set the X axis extent to 55 meters and the Y axis extent to 12 meters. You can also change the increment size of the axes labels by toggling off the Auto Increment Size button and changing the increment size for each axis. For this analysis, I will simply leave the Auto Increment Size for this axis on. As you can see in the background of the page on my screen, there is a grid already activated. You can go to Set, Grid to turn this grid off or on, activate Snap to Grid, or change the grid spacing. You can use the zoom options along the bottom bar of your screen or under Set, Zoom to change the view of our analysis, either to the extents of your domain or the extents of the work area page, or simply zoom in or out. It can be helpful to first sketch the problem prior to defining the geometry of the domain. For developing a polygon, we can use the Sketch Polyline button and draw the outer dimension of our embankment domain. The Escape button or right mouse click can be used to deactivate the Draw Polyline command. Lines can also be drawn to indicate objects that are not included in the analysis, for example, the water level on one side of the embankment. Arrows, circles, and arcs can also be drawn on the working area as visualization tools. These sketches are not included in the domain or the analysis and can be moved, modified, or deleted using the Modify Objects command. The approach to use when developing a numerical model is to determine the geometry, assign materials, assign boundary conditions, and then, finally, to review and fine-tune the finite element mesh. Let's start by creating a domain. I will go to Draw Regions and draw my embankment region following the sketch of my embankment. Here, points will automatically be made wherever I use the left mouse button to click on the working area. Once the region is created, I can either draw a second region or use the right mouse button or the Escape button on my keyboard to stop the Draw Regions command. We will add in more geometry points along the lines where our boundary conditions will be applied. For example, at the height of the reservoir, we will add a point to the embankment region so that the boundary condition is not applied above this point. Next, we will add the material to our analysis. I will go to Key in Materials to open the Materials Define window. I will add a new material and give my material a name. I will then choose the Saturated Unsaturated option from the drop-down menu. Here, I can create a hydraulic conductivity and volumetric water content function for each of my materials. The Saturated Only option can be used if a steady-state analysis is conducted on a domain that will remain saturated for the entire duration of the simulation. If unsaturated zones are expected to occur, as is the case in our current analysis, the Saturated Unsaturated option is required. In this case, the volumetric water content function is not required as I am not conducting a transient analysis. This means that there will be no change in storage within the domain. However, to use the internal estimation algorithms for the hydraulic conductivity function, a volumetric water content function is required. So, I will set up a volumetric water content function by clicking on the ellipsis button. This button is used extensively in GeoStudio to indicate that the additional features can be accessed. We will then add a volumetric water content function and give it a name. We will then choose the VWC data point function option and use the internal estimation algorithm by clicking on the Estimate button. I will use a saturated water content of 0.5 and choose the silt sample material. This creates a typical silt volumetric water content curve based on published literature with a saturated water content of 0.5. If desired, the Edit Data Points option can be activated and data points within the curve can be deleted, moved using the left mouse button, or edited manually within the given point list. Points for the curve can also be added by pasting the points into the list area, provided the appropriate columns are copied from a program such as Microsoft Excel. The fit of the curve to the data points can also be edited using the Curve Fit and Segment scroll bars, which may be useful if the curve of the function does not pass through the desired data points. The coefficient of compressibility will also be changed to 5 times 10 to the negative 4, 1 over kilopascals. Since I am happy with my current curve, I will choose it from the drop-down menu for the volumetric water content function. Next, I will add the hydraulic conductivity function by clicking on the ellipsis button. I will add a hydraulic conductivity function in a similar manner as I did with the volumetric water content function. I will use the internal estimation algorithms, again, by clicking on the Estimate button. I will use the Van Genuchten estimation method, choose my volumetric water content function from the drop-down menu, set the saturated hydraulic conductivity to 1 times 10 to the negative 6 meters per second, and the residual water content to 0.05. Once created, I can choose the Edit Data Points option again to see how my curve fits my data points, or move my data points with the left mouse button. Since my curve passes through all data points nicely, I will now go back to the Key in Materials window and choose my hydraulic conductivity function from the drop-down menu. If I wanted to create an anisotropic material, I could change my KY to KX ratio. Here, a value of 1 indicates that my vertical hydraulic conductivity is equal to my horizontal hydraulic conductivity. If my material actually required a vertical hydraulic conductivity of 1 times 10 to the negative 7 meters per second, I would change this ratio to 0.1. The rotation option allows you to change the hydraulic conductivity direction if it is not in the X to Y direction. Lastly, the Activation Pore Water Pressure option allows you to choose a specific pore water pressure for the entire material when it first becomes active in the simulation. Now, we will add the material to our domain by choosing Draw Materials. We will simply choose the embankment material and assign it to the region. Boundary conditions can be created and assigned in a similar way as the materials. I will choose Key in Boundary Conditions to open the Define Boundary Conditions window. Here, 2 boundary conditions are automatically defined by default. These are the potential seepage face and zero pressure boundary conditions. The potential seepage face boundary condition can be used where you want the solver to locate the position where a seepage face may develop. This means that the solver will create a zero pressure boundary condition where the pressure of the nodes becomes greater than 0 kilopascals. The zero pressure boundary condition applies a constant pressure of 0 kilopascals or a constant pressure head of 0 meters at the chosen nodes. I will now add a new hydraulic boundary condition to represent the reservoir level in our analysis. We will set the new constant head boundary condition to 11 meters. You can also change the color of your materials or boundary conditions by clicking on the Color Set button while the item is active. Now we can open the Draw Boundary Conditions window. We can add the reservoir head boundary condition along the line representing the reservoir and the seepage face boundary condition along the downstream side of the embankment to allow water to pass out of the domain if the pressure exceeds 0 kilopascals. We will also add a zero pressure boundary condition at the node representing the toe of the seepage face. Note that the boundary conditions can also be applied to regions depending on the requirements of the analysis. Our last step of developing our numerical analysis is to view our finite element mesh. You can view the finite element mesh by choosing Draw Mesh Properties. Here we can see that the default mesh is set to have an approximate global element size of 1.5 meters. We will create a finer discretization for the global mesh by changing this value to 1 meter. Mesh constraints can also be applied to individual regions, lines, or points, but it is recommended to start with a simple mesh and then constrain the mesh only as necessary. Now we can solve our analysis by toggling on our analysis in the Solve Manager window and clicking on the Start button. Once solved, the window will automatically change to the Results view instead of the Define view. By default, the total head contours, velocity vectors, and phreatic surface within the domain will show once the analysis has been solved. The Results Time window allows you to see what time steps have been solved and allows you to view the contours within the domain for different time steps. Since we are conducting a steady state analysis, there is only one time step available of 0 seconds. You can change the contours that are being shown on the domain in the Results window by choosing a different contour type in the drop-down menu. You can also add new contour options by clicking on the Draw Contours button. You can change the shading methods used to draw your contours, add a legend, or change the increments and starting and ending values of your contours. Other items can be added by clicking on the Add button and choosing the type of results contour you would like to create. For example, I can choose Material Properties and view the resulting X or Y conductivity contours for my analysis. This will add the new Contours option to the drop-down menu in the Results window. You can also add contour labels to your domain by clicking on the Draw Contour Labels button. Then you simply click on the contour line where you would like the labels to be painted. Another useful tool in the Results view is the Draw Vectors button, which allows you to turn on or off the velocity vectors that are shown on the domain. Here, you can change the maximum vector length or magnification of the vectors. Flow paths can be drawn on the domain if desired. These represent the path that a drop of water would travel from the reservoir through the embankment. You can click with the left mouse button to create a flow path anywhere within the domain and remove it by clicking on the same location a second time. Remember, flow paths are not the same as flow lines. You can choose what items are activated in the Results window at any time using the View Preferences toolbar along the right side of the screen. Here, you can toggle on or off results information such as the flow paths, velocity vectors, contours, or you can view your mesh, boundary conditions, material properties, or toggle on and off geometry items such as the regions or region numbers. There are also other options that can be used to view result information within the Results window. For example, you can view Object Information, which outlines information for each geometry item, such as the boundary conditions applied to a line or mesh properties of a region. The View Result Information button opens up a window that can be used to view result information for a node, flow path, Gauss region, and so forth. This information includes coordinates, pore pressure parameters, water flow parameters, material properties, and convergence results. This can be useful when analyzing specific nodes or points within the domain. The View Report button can be used to develop a report of the input data and will open the report in an HTML format. This gives you all of the information regarding the input data, geometry, and other information from the analysis. You can also view result information by clicking on the Draw Graph button. For a seepage analysis, the conductivity versus matrix suction graph is automatically added to help the user analyze convergence of the analysis. This graph indicates if the simulated hydraulic conductivity matches the function that was entered into the Key in Materials Define window, indicating that there are no convergence errors related to the conductivity functions. To add a new graph, I will click on Add and create a graph showing the pore water pressure profiles along a line through the embankment. I can choose nodes by clicking and holding down the left mouse button and dragging a box across the desired nodes within the domain. Another option is to hold down the Shift button on my keyboard while using the left mouse button to click at the start and end of a line. This will choose nodes along the mesh where this line intersects. Another option is to choose a geometry item as a location, which will allow you to choose nodes within regions, along lines, or at points of the domain. You can choose multiple geometry items by holding down the Control button while clicking on the left mouse button. I will choose to create a graph based on a line through the middle of the domain. This will create a pore water pressure profile through the middle of the embankment. I can now choose to change the x-axis to plot elevation since the line I drew for my locations was in the vertical direction. I can also use the More button to copy the graph image so that it can be pasted as a picture into another program, the graph data as tab delimited columns, which can be pasted into another software like Microsoft Excel, or exported as a separate comma delimited file. I can change the visualization of my graph by clicking on More Options. Here I can customize the labels on my graph, change the scale of my axes, rotate my graph so that elevation is on the y-axis, add or remove a legend, change the style of my lines, or change the font of the text on my graph. Now, let's say we wanted to know what would happen to our phreatic surface if we turned on a drain along the toe. We will return to the Define view and open the Key in Analyses window. Here, we will clone our current steady state analysis so that the current material properties and boundary conditions are copied to the second analysis. This adds a second steady state seepage analysis to our analysis tree. Multiple analyses can be added to the analysis tree to allow the user to solve multiple scenarios within the same project file. The geometry of the domain is considered project-specific, but the material properties and boundary conditions can be modified to simulate different scenarios of the analysis. Another option is to create a transient analysis of the embankment using the steady state analysis as the initial conditions. As an example, let's simply change the boundary conditions of our initial analysis to see what happens when a drain is present below the toe of the embankment. I will change the name of my analysis so that we know which analysis in the analysis tree has the drain present. Next, we will add a point at the extent of the drain that we will add along the bottom of our embankment near the toe of the downstream side. I will now go to Draw Boundary Conditions, add the zero pressure boundary condition along the line representing my drain, and remove the potential seepage face boundary condition from the downstream line of the embankment. I will keep the material properties and reservoir head level the same. Next, we will create a finer discretization of 0.5 meters along our toe drain as well, as our phreatic surface is expected to exist somewhere along this line. I will do this by highlighting the line representing my drain, choosing Length of from my drop-down menu, and entering 0.5 meters as my desired length. This time, I will also add in a flux section through the middle of my embankment. Flux sections are used to identify elements where you want the software to compute and report the amount of flow crossing these elements during the solve process. I will now return to the Solve Manager to solve this new analysis of our embankment. The results view will automatically open since I am solving the analysis highlighted in the analysis tree. The settings that I had set in my previous analysis in the results view have been saved, so I can now see my updated pore water pressure contours, flow paths, and phreatic surface. We can see that the drain under the toe of my embankment is forcing water to leave the domain along this line, changing the position of my phreatic surface. I will add a label to my flux section so that I can view the amount of flow crossing this section of my embankment. Note, if at any time you are unsure in your understanding of the dialog boxes, you can simply click on the question mark in the top right corner of the dialog box, use the Help tab, or use F1 on your keyboard to access the online help. If at any time you would like to view the engineering book for the product you are using, and do not want to return to the GeoStudio Start page, you can simply click on the Home button on the online help. We have now reached the end of this introductory tutorial. Note that not all of the powerful features of SEEP W 2012 have been used or discussed here. Further information on each command can be found in the online help, supporting documentation for SEEP W, as well as in other tutorial videos of the Getting Started with GeoStudio video series. Thank you for watching.